This is the first derivative test where you find local extreme values. The theory behind the first derivative test is you suppose that c is a critical number of a continuous function of f. If the derivative of f changes from positive to negative at c, then f has a local max at c. If the derivative changes from negative to positive at c, then c is a local min. If the derivative does not change at c, then there is no local extreme values. So these are the steps. Step 1. Find the derivative. Step 2. Set the derivative equal to 0 and solve for the critical numbers. Step 3. Use the intervals between the critical numbers and endpoints. Choose a point in each and plug it into the derivative. Write down the sign. If it is positive, the function is increasing. If it's negative, the function is decreasing. Step 4. If there is a sign change between the critical points, then use the theory found in the first derivative test. In step 5, plug in the max and min values into the function to get the y-coordinate.
Nobody to hear my song, so I'm humming to myself.
This is example 19, the first example, where we have to find the local max and min values in the function 2x cubed minus 3x squared minus 12x. We have to find the derivative, which is 6x squared minus 6x minus 12. Second step, we have to set it equal to 0, and so when we get all this out, we end up getting critical numbers of x is equal to -1 and 2. Step 3, we use intervals made from our critical numbers and endpoints to find where the derivative is positive or negative and if the function is increasing or decreasing. For example, we have negative infinity to -1, where the derivative is positive and so the function is increasing. We have -1 to 2, where the derivative is negative and so the function is decreasing. And we have 2 to infinity, where the derivative is positive and the function is therefore increasing. In step 4, we find sign changes at the critical numbers to determine local maximum minimums. In this example, since there's a sign change from positive to negative at -1 is the local max. And also, since there's a sign change from negative to positive, at 2 is a local min. In step 5, we plug our local extremities into the original equation, and so at f of -1, we have that equal to 7, so there's a local max at -1, 7, and at f of 2, we have it equal to -20, so there's a local min at 2, -20. In this next example, we have to find the local maxima and minima of g of x is equal to 200 plus 8x cubed plus x to the 4. In step 1, we have to find the derivative, and the derivative is equal to 24x squared plus 4x cubed. Step 2, we set our derivative equal to 0 and find the critical numbers of -6 and 0. In step 3, we use the intervals with our endpoints and critical numbers, and for this example, we have the interval -infinity to -6, where the derivative is negative and so the function is decreasing. We have the -6 to 0, where it's positive and increasing, and 0 to infinity, where it's positive and it's also increasing. In step 4, we use sign changes at our critical numbers to find local extreme values. And so there's a sign change from negative to positive at x equals to -6, and so -6 is a local min. There is no sign change at 0, and so 0 is not a local extreme value. And so in step 5, we plug -6 into our original equation and get -232, and so we have a local min at g of -6 equals -232. In our last example, we have to find the local max and min values of f of x is equal to x cubed plus 5. In step 1, the derivative is 3x squared. In step 2, we set it equal to 0, and we find a critical number at x equals 0. In step 3, we find the intervals, and so in this example, from -infinity to 0, the function is increasing, and from 0 to infinity, the function is also increasing. In step 4, there is no sign change at a critical number. So in step 5, we conclude there are no local max or min values.
So you forgot.